Still the 17th of October. Pull out that periodic table and take a look at it and find nickel. Nickel, one of the magnetic triad, one of the three elements, which is known to be magnetic, present in the Earth's core. Pretty cool stuff. Stick your finger on nickel. Ni. Haha. Give me a nickel. Now, you've got nickel firmly in sight. Let me ask you this. What's the mass of an atom of nickel? Oh, that's the perfect answer. Thank you, sir. Someone says 58.6934. Anybody got a problem with that? AMUs, of course. You got a problem with that? You got a problem with that? I don't do that very well. I got a problem with that. What's my problem with that? Talk amongst yourselves. Can we have a half, can we have a 0.69, whatever the heck that was, atom of nickel? No! You got an atom of nickel or you don't got an atom of nickel. There's no partial measures here. So why are the atomic masses not whole numbers? Because somewhere along the line, probably in physical science, definitely in middle school, you were taught, well, you just round to the nearest whole number. That's the mass. That seems a little bit sloppy to me. Can you have a part of an atom of carbon, a part of an atom of nickel? Well, I already said no, so why are they not whole numbers? Talk amongst yourselves. So, those are not exact masses. Those are averages. They're weighted averages. Because remember, we have isotopes. So, for instance, we can have atoms of carbon that have a mass of 14 AMUs, C14. We can have atoms of carbon that have a mass of 13 AMUs. And we can have atoms of carbon that have a mass of 12 AMUs. And based on how many of each of those atoms there are, we get a weighted average. So if I take a sample of pure carbon, if I take a candle and I burn it up against something and I get that black soot and I scrape that down and I had the sort of lab analysis equipment to go ahead and average, I would find that some percentage, and I'm totally making up numbers here, do not quote me on these, maybe 97.99% of all the carbon atoms I found had a mass of 12. And maybe 0.25% of all carbon atoms I found had a mass of 13. And whatever's left over, I don't know, 1 point something, had a mass of 14. So we take what's called a weighted average. We multiply, remember these numbers are all made up, they are nonsense numbers. The masses are real, but the percentages are totally fake. We take the masses and the abundance and we get what's called a weighted average. So very often, that trick that you learned in middle school and probably continued in physical science where you round to the nearest whole number and you say, well, that's the most common isotope. That often works. Go ahead and take a look at carbon on your periodic table. So if we look at carbon, we have an weighted average atomic mass of 12.0107. What do you think the most common isotope of carbon is? Carbon-12. Now, I wasn't making that part up. I don't know what the actual abundance is. Let's look at sodium. What do you suppose the most common isotope of sodium is? Yeah, sodium-23 is fairly common. Take a look at cobalt, if you would be so kind. What do you think the most common isotope of cobalt is? It looks like it should be 59. I'm not sure. there are some elements where, in fact, the nearest whole number is not the most common isotope, where it might be, there's a lot of cobalt-58 and a lot of cobalt-60, and it averages close to 59. The only way to verify those is looking them up. You're never going to remember those. There are a few that stick out in my mind as weird as like, oh yeah, you think it's argon-40, but really it's argon-39 and argon-41 or something. So it's not always a guaranteed trick, but it's not a bad trick. Now here's the bigger question. How do we find a weighted average? So I'm going to take a left turn, and I'm going to use what has become over the years my favorite metaphor for this, which is gas prices. Okay, how many of you have filled up a gas tank in the last month? Okay, I live in Pennsylvania. I only fill up in Ohio because gas is 40 cents a gallon more once you cross the state line, Pennsylvania state taxes. Let's say you're driving around Calcutta, East Liverpool. Actually, you could just do 170. And there's, what, 1, 2, 3 gas stations within a mile, roughly? So let's say that we have one whose price per gallon today is $2.49, one today whose price per gallon is $2.45, and one whose price per gallon is $2.41. You know how to find the average, don't you? Go, find the average. I get an average of $2.45 a gallon. You probably got the same thing. Now, I put in here the sort of generic formula for finding averages. Price 1, price 2, price 3 divided by the number of samples you've got. In other words, add up your values, divide by the number of values you have. Easy enough. Well, what if I expand my search area? And, it starts to look like collusion, but I have 3 stations charging $2.49, 2 stations charging $2.45, and 1 station charging $2.41. Will this change my average? Yes. So how would I find that average? Well, I can take that generic formula, price 1 plus price 2 plus price 3. I can keep adding pretty much forever. That would look like this. It looks something like that, right? 249 plus 249 plus 249 plus 245 plus 245, blah, 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 blah. Is there a way to shortcut that? What is repeated addition? Multiplication. So we can do this. 3 times 2.49 plus 2 times 2.45 plus 1, which obviously we could really skip, times 241. Divide the whole mess by our 6. That was our old average. And making liberal use of parentheses on your calculator really helps here. Okay, I get 2.46333. All right. Well, now, what if I was feeling really ambitious? I was doing a project for some sort of bizarre statistics class someplace, and I went out and I surveyed 100 gas stations. Okay, so I survey 100 gas stations, and I get data. I'm going to get rid of my old calculations here. Well, actually, I'm not going to get rid of them all. I'm going to get rid of this. I'm going to get rid of this. I'm going to get rid of this. And I'm going to get rid of my extras. And what if I find that 72 gas stations are charging $2.49 and 20 gas stations are charging $2.45. What does that leave me with? 8 gas stations are charging $2.41. So my total number of samples here is 100. Well, knowing this little shortcut here, I can say, okay, well that is, in fact, 72. Let me blow this up a little bit. 72 times my 249 plus 20 times my 245 plus 8 times my 241. Well, how many samples did I say I had? 100. Huh. Well, would that mean that I could actually do this? 72 divided by 100 times 2.49 plus 20 divided by 100 times 2.45 plus 8 divided by 100 times 2.41. Could I do that? You betcha. Something divided by 100 is what? Percentage. So what I can actually do is take the individual value times the percentage of stations that have that value, and I get a weighted average. So let's find our weighted average here. Let me shrink that, move that up. We call this a weighted average. It doesn't matter if you have 100 pieces of data or 1 billion pieces of data. You're just looking at the percentage of pieces of data with a given value, and your weighted average is the value times the percentage of your data that has that value. So, 0.72 times 2.49 plus 0.2 times 2.45 plus parentheses 0.08, be careful, times 2.41. What do you get for your weighted average? You should be calculating. I get $2.4756 per gallon. Now, how many sig figs do we have? 3. We're going to assume that our percentage values have infinite sig figs. But in terms of our measured price of gas, so our correct recorded answer with sig figs would be a weighted average of $2.48 per gallon. Now, we're going to do this with atomic numbers, because that's where this really matters. So I'd like you to flip that sheet over that I gave you earlier. So I apologize for not having left you more space. It would have been helpful, I realize, but, well, I'll fire my practice sheet writer. So we want to know what the average atomic mass is for some element which exists in the following isotopes. 89.5% of it has a mass of 60.0 AMUs, 9.75% of it has a mass of 58.0 AMUs, and 0.75% of it has a mass of 61 AMUs. Now, I'm going to tell you where the most common pitfalls on these kind of problems are, because I've fallen into them, so that way you can avoid them, because I know where the potholes are. I've stepped in every single one of them repeatedly. You don't need to step in the same pothole I did. Our general formula here is the mass of the first isotope times the percentage of the first isotope plus the mass of the second isotope times the percentage of the second isotope. This is a useful thing probably to add to your notes, actually. Plus the mass of the third isotope times the percentage of the third isotope. And that's equal to the weighted average atomic mass. Okay. It's useful to have that formula because in some of the other problems you're going to be asked not for the weighted atomic mass, but for either the mass or the abundance of one of the isotopes. So having that formula means you can rearrange it to solve for any one of those variables. But starting with this one, we've been given the mass of the 3 isotopes, we've been given their abundance, so we're just going to go ahead and plug them in. So the mass of the first one that we're given is 60.0 AMUs, and its relative abundance is 89.5%. We need to express that as a decimal, so that's 0.895. And I'm going to bracket that because it keeps life a little bit simpler. The second isotope that we were given has a mass of 58.0 AMUs and a relative abundance of 9.75. That's 9.75 divided by 100. So that's 0.0975. That's one of the traps. I generally, when I'm setting these things up, I will actually write 9.75 over 100 so that I don't screw it up. And the third isotope has a mass of 61.0 AMUs and an abundance, oh boy, of 0.75. And I'm going to actually do this on my calculator. 0.75 divided by 100 because I always screw these up. So 0.75 divided by 100 is 0.0075. All right, now it's just a matter of doing the math. And use the parentheses button on your calculator for the love of Pete. All right, so we have 59.8125 AMUs is the raw number. We have 3 sig figs based on the given masses. So we get a final answer of 59.8 AMUs once we sig fig. That's it. The next one is one where you are calculating for the abundance of an isotope. I would actually suggest that you do 12 and 13. I would suggest you do 12 and 13 first and then come back to 11 because 11 is a little bit trickier. That's it. Key will be up on Classroom in a matter of minutes. So go.